Hello everyone, welcome to the second segment of video on the map series. In this video we discuss certain things related to the datum in the GCS. Just to remind you, GCS represents the geographical coordinate system. When we say certain things related to a datum is simply a foundation and reference for spatial measurements. A system of coordinates is then used to describe those measurements relative to the datum, and a projection is the visual representation of those measurements on a different surface. Hence, the datum is part of the geographical coordinate system that determines which model is used to represent the Earth's surface and where it is positioned relative to the surface. Now, the part of the problem which attracts here would be the Earth's surface is not perfectly smooth around as we approximate it to the geometry of a sphere or a spheroid or ellipsoid. There are many different datums designed for different parts of the world. Refer to the first picture. The reality of Earth is something like this. We try to approximate the surface of the Earth in terms of a geoid, and the other approximation is ellipsoid, and these two represent some sort of simplification of the surface of the Earth, but the reality is something different. We see some undulations. Now the terrain surface is represented either with the help of a geoid or some other sort of ellipsoidal shapes. Hence, a datum defines the position of the spheroid relative to the center of the Earth. It provides a frame of reference for measuring locations on the surface of the Earth, and hence, it defines the origin and orientation of latitude and longitude lines. For example, if I consider a perfect sphere as a reference frame and the sphere center as origin of the frame, you can just visualize the system in this way. Now we have theta and phi being the angles. One is horizontal, the one is vertical angle. Now the positions are defined with the help of x, y, z. As you can see here, x is r plus h cos theta into sine phi, y is r plus h into sine theta into sine phi, and z is r plus h cos phi. With all these narrations, one could say that a datum is built on top of the selected spheroid and can incorporate local variations in elevation. With the spheroid, the rotation of the ellipse creates a totally smooth surface across the world. Because this doesn't reflect reality very well, a local datum can incorporate local variations in elevation. Hence, there lies certain advantages as far as local datums are concerned. Now, here is an example which tries to depict the major axis, minor axis, origin, and flatness kind of variations associated with the two sets of datum. One is the well-known World Geodetic System 84, the Earth-centered datum, which is reflected in the blue color, this one. Other one is local datum, which is North American datum 27. Now, as I said, the AB, the major axis, minor axis, and the origin, they really vary here. You can see the variations here. You see some kind of eccentricity, and based on that, the flatness which they represent, certain things related to the surface of the Earth also vary. So just to summarize before we wind up, the datum is a part of the GCS that determines which model is used to represent the Earth's surface and where it is positioned relative to the surface. Since the Earth's surface is not perfectly smooth around, there are many different datums designated for different parts of the world. Uh, just to differentiate it from the GCS system, A GCS is the full definition of how to tie coordinate values to the real locations on the Earth. In addition to a datum, a GCS includes a prime meridian, which stands for 0 degree longitude, and an angular unit, which are often expressed in terms of degrees. Our next segment would be to deal with something related to the projection in the PCS, the projected coordinate system. Thank you.